sort of who I am, and just give a little bit of professional context just so it gives me a smidgen of credibility to be having this conversation. And then kind of tell you how I ended up here tonight, which is actually the funniest part about this is how much I've been able to add to that story in the last 24 hours as Daryl has explained his true intent with more and more detail as we got close here. So I'm definitely winging it. But so I did not, like almost probably everybody, I didn't grow up in San Diego. I ended up moving here for my postdoctoral fellowship. So I'm originally from the Midwest and grew up on a farm. And actually one of the ways that I ended up in this congregation is that this was, when we moved here, you know, you have to find a new church and everything like that. And this was a church that, although this may sound a little bit superficial, physically reminded me on the inside of exactly the church that I grew up in. And so it was a very homey feeling just when I first saw it with no people in it, and then the, you know, the people and the community life was even more welcoming. So that was actually sort of an easy, sort of very familiar and comfortable feeling place that really, you know, came to be more home-like as time went on. So professionally, how I ended up sort of being able to, I guess, partially give this talk is I'm a scientist. I originally was a chemist in terms of my undergraduate and graduate work. I currently, now the good thing you told me this was going to be on YouTube audio because I won't say who I work for, but I run the cardiovascular and metabolic disease research for a pharmaceutical company. And we have 4 major laboratory sites in the world. One of them is here in San Diego. So I run the CVM area for that. But in addition, I've been obviously a lifelong member of a religious community, and it's been interesting to me over the last several years, and particularly, I guess, once I became sort of an adult working scientist who had not sort of moved away from my religious upbringing, how often I found myself in a situation where you have these sort of very polarized, kind of abstracted media views of a sort of a separation and almost adversarial type relationship between sort of a life of faith and a life of sort of being grounded in a scientific worldview and understanding. And you know, it was always very kind of a very dissonant experience for me to sort of see that image mostly in popular culture and the media, but yet also feel that, you know, hey, on the other hand, I'm actually probably one of the, you know, I'm actually a working scientist who also has a spiritual life. And I never actually found that to be that, you know, it's a nuanced relationship, but I never found them to be incompatible. And actually, the majority of my fellow working scientists, I think, are often in that same boat. And so it really struck me as being something that was almost a caricature that was convenient for a lot of reasons, but wasn't necessarily reflective of those people who actually attempted to sort of bring those two worldviews together. And so that's kind of been a long-standing interest of mine. And so that, you know, mostly involved just my own, you know, amateur intellectual pursuits in my off hours, kind of a, you know, nights and weekends life. But then when Daryl joined the congregation, I think, I don't even know how we ended up initially communicating about this, but came to appreciate that Daryl also was very interested in this concept and this sort of dialogue between sort of faithful and scientific views of the world. And so, you know, we just mostly were on a personal level of casually discussing this, and then eventually decided, you know, maybe this is something that could be a little more public, and this is certainly a long-standing interest of Daryl's, and maybe I could help get that started. So that's sort of how, you know, I think I ended up here tonight. And I'll give my disclaimer that the reason I noted what I do is this is long out of my actual working job, and so I'm going to be relying on my, you know, many years ago background in chemistry to give this talk, but it should be enough, I think, to sort of provide a sufficient reference. And so what I thought I could do is maybe provide, and this is again sort of just a kind of a very basic level of, you know, during Lent, Daryl's going to make a focus on the role of water and the sort of various ways in which water is special and unique in spiritual life. And tonight I thought I could just maybe also talk about, kind of at a basic level, how water, irrespective of whether one has various different spiritual belief or no belief at all, that one just believes that, you know, the earth is a basically inert floating rock in space and has certain things on it. No matter what view of the universe you subscribe to, you'd still view water as a very special of thing in the universe. And so I did think it was important to say, however, what does that mean to say that it's special. And so this is the heaviest that this talk is going to get, and I encourage you to stop me and ask me to explain it if it doesn't make any sense. But most of you would recognize this thing here. It's the periodic table. And the periodic table is basically a way in which scientists organize all of the elements that are known in the universe. And those elements are organized here, and I made it deliberately small enough so you couldn't be distracted by actually trying to see the content. I just want you to understand two things about it, because this is basically, if you knew nothing else about chemistry, you would already know quite a bit by knowing this. One is that the order going from left to right matters, and it matters by sort of increasing trends along certain characteristics of various elements. And then the other is that top to bottom matters. And generally speaking, things on the top are very small, things on the bottom are very big, and in between, things are going from small to big. And that's basically all you really need to know about the periodic table. Now, each of these little boxes is what's called an element. And an element consists of a pure sort of atom. An atom is basically the smallest indivisible amount of matter that you can have. And then a molecule is essentially the combination of two or more atoms. So that's as heavy as it's going to get right there. That's the limited chemistry that you need to know. And so what do we mean when we say that water is unique? So the other property of the periodic table is that things that are near each other are like each other. And as you move either horizontally or vertically, whatever properties they have, they vary sort of in a linear fashion. And so basically things that are near each other are clumped near each other because they're like each other. All know probably has two components to it, H2O. We've all kind of heard that. You see it in the store, you see it on water bottles and everything. So H is hydrogen, O is oxygen. There's a lot of things that are put together as something plus two hydrogens. They're all called hydrides. Hydrogen sulfide, hydrogen oxide, water, and various other things. And water, amongst all those molecules, is very unique in its properties, and I'll go into those in a second. So that's kind of striking. Even if you had no belief in anything other than chemistry, you would still identify water as unique, because it is very unusual for its place amongst those types of molecules. And the other thing is that unusual about is, irrespective of what the various atoms are that are in a molecule, if you just look at its size, and typically molecules' sizes dictate kind of in part their properties, it has very unusual properties for its size. And we usually talk about the size of molecules in terms of their weight. So it's just like we have a weight, and a chair has a weight, a car has a weight, a molecule has a weight, and it's defined as its molecular weight, of course. It doesn't really matter what that means specifically, but basically the weight of a molecule is essentially its size, and the size drives in large part its properties, in addition to whatever the specific components are. Both where it is amongst these trends, so it's unusual in what it looks like within the trend, and it's unusual for its size. And so that's what we mean scientifically when we say water is unique. And then just kind of descriptively, and this starts to take us a little bit more towards the topic, is that for a lot of reasons that are way too complicated to explain, and some of which aren't even fully understood, water is actually the only common element, or the only common molecule that actually exists in all three states of matter, so solid, liquid, and gas, naturally. You can force a lot of things in the laboratory. In fact, we can force most things in the laboratory to exist in all those states. But if there wasn't a speck of life in the universe, water on Earth would naturally exist in all three of these states. And almost no other molecule that's commonly found is that true for. And so that's unique as well. And so that's really kind of what we mean by it being a unique thing, irrespective of anything having to do with spirituality or whatever. So then I thought, maybe just pause, because I don't have that many slides, and I got to fill an hour here. So any questions about anything I just said before we kind of go into some of the specifics? And am I pitching this at the right level? Is this too detailed, not enough? Okay, so now we'll do the fun stuff, and you can always walk me back to this slide if you want more explanation. I should actually tell you, for for many years, I would go to scientific conferences or medical conferences, and I would never ask a question. And then several years ago, I finally came to this decision, you know what? I'm going to spend my whole career being a non-entity at these meetings unless I force myself to ask a question. So ever since then, I've had a rule. I have to ask at least one question every meeting I go to. So I'll let you guys decide whether you want to follow that rule or not. So now I'm going to talk about certain things that make water kind of unique, essentially more for life. So one of the things that water is unique about, I'm not going to talk again about what I mean by unique, I told you that in the previous slide, is that water is really unusual, and in fact is unusually good at dissolving things. And it's actually, what dissolving means, basically the simplest thing is you take salt or sugar and you put it in water, you stir it up till it disappears into the water. It's dissolved. That's dissolution. So you can put solids into lots of liquids. But water is really unusual in being able to dissolve lots of things. So water can dissolve things that are very, very small and simple, like salt, table salt, other kinds, rock salt, sea salt, all that kind of stuff. Water can, and many liquids can't do that, in fact. It won't dissolve a salt in them. Water can dissolve simple sugars, so glucose, other sort of starches or simple starches, water can dissolve all of them. And again, that's something that, for its size and place in the periodic table, is unusual for most liquids. Most liquids won't do that, actually. And then more importantly for us, these are actually, salts and sugars are very, very small molecules. Things like proteins or fats or amino acids, which are the components of proteins, or hormones that tell our body what to do and not do, or neurotransmitters. Water can, and these are all, it's too detailed to go into right now, but these are all really complex, actually quite large molecules on a molecular scale. And water dissolves all those very well. And if that wasn't true, there basically would be no way that we could take all of these very complicated components of even just the simplest cell, the simplest bacteria or virus on the planet, is already very, very complicated. It already has thousands and thousands of components that all essentially have to interact with each other in some organized way that responds to the environment, that's capable of dividing and replicating and propagating that thing. All requires the ability of those things to all essentially be kind of in solution and interacting with each other. And water can do that. And there's actually very few other liquids that are known that are at all common that can do that. So water is very unique in that way. Any questions on that slide? Nope. All right. Tough crowd. So this is probably one of the sort of the bigger things that everybody knows, but maybe something that's not necessarily thought of about being important. So I have to admit, I don't know exactly what I was or how far into my education when I learned this, but in fact it's very unusual for a liquid when it freezes down into a solid to float. For most other liquids, when they get cold enough to actually freeze, they sink. Water is very unusual in that respect. And so that just kind of seems like an interesting fact that you wouldn't necessarily care about. That's interesting, but what does it really matter? Well, if you imagine that if you had a body of water, like a lake or an ocean, and there was life in that water, or there wanted to be life in that water, or maybe there someday could be life in that water, when it got cold, which at a minimum it happens at night, and more often for almost every planetary body has a certain distance from its star, and those are never perfect circles. So if some period of time it spends a longer distance from its star than other times, and that longer distance means less energy from the star, means cold. And so invariably things are going to freeze. Solid was heavier than the liquid, the solid would sink to the bottom, and then essentially what would happen is that liquid would freeze from the bottom up. Off the top of that body of water from the cold atmosphere. And that prevents all the liquid below it from actually freezing, because that now layer of solid of ice is an insulator, and it protects. Even if the temperature above that solid went down 100 more degrees, the liquid below that solid doesn't feel it until that solid is actually cooled all the way down, and basically that never happens. And so that layer of liquid below is protected. And more importantly than for water, like every liquid, this is true for every liquid, is that colder liquid gets a little bit closer together, so it's a little more dense, and so it sinks. So what happens in a body of frozen water, even though it feels extremely cold to us, a layer of relatively warm water. And that allows life to survive throughout a winter or throughout a cold period, because eventually it would all freeze and there would be no liquid. And so nothing can survive in solid liquid. So this is really an important property. If this wasn't true about water, it's very, I think most scientists would tell you, it's very unlikely there could be life on Earth, because it would never have survived long periods of extreme cold where there was no liquid. And depending on what you believe about how life originated, if you believe that it, through some path involving simpler organisms, came to be, that it's virtually impossible that could have ever happened, because that almost certainly happened in water. So I'll pause there and see if there's any questions. Not so much. All right, it's going to be a fast hour, Daryl. So this is related to the previous one, and it's interestingly enough, it has the same concept. It has nothing. The underlying physical properties of water that drive these two things are completely different from each other, but they both are extremely important when it comes to this issue around life in water. So the other interesting property about solid water, or about water, is that most people in an average life, they really have exposure to kind of two types of liquid. Water and water-based liquids, whether it's water or milk or beer or whatever. Oh, three, I'll take it back, three. Alcohol of various kinds, rubbing alcohol, this and that. The alcohol you drink is actually mostly water. And then things like gasoline, things that are complex mixtures of carbohydrates, or of hydrocarbons. We don't really think about kind of properties of water versus other things, but one of the things that's really unusual, again, about water, that we all know that if you take a liquid like water and you take all the heat out of it, it eventually freezes. And if you add a bunch of heat into it, it eventually turns into steam, it vaporizes. But if you actually did that, and you did that with like 5 different types of liquids, or even 3 different types of liquids, but 5 is probably better, you would immediately come to see something really, really interesting, which is that if you took the equal amount of heat that it took to take all those other 4 liquids and make them into gases, and you put that same amount of heat into water, it would do nothing to water. Water would warm up, but it wouldn't actually change into a gas. Conversely, if you somehow had some magic machine that could suck the heat out of all the other liquids until they froze, and you took that same amount of heat and you sucked it out of water, water would not freeze. There's a technical term for what that means. It's called the heat capacity. But the practical, or the simple way to understand it, is that water is really good at resisting changes in its own temperature that would cause it to change phase. So it takes lots of heat into water to make it vaporize. It takes a lot of heat out of water to make it turn into a solid, much more so than other liquids of its size. And so it's very unusual in that respect. And so the reason that's important, that's probably, imagine that, we all like kind of 70 degrees Fahrenheit, but most things that live in water live around 40 degrees. And if the heating and cooling of the earth or the environment or whatever change the water fluctuation up and down a lot, life would have a difficult time surviving, because it would be, if you had a situation where there's constant heat bearing down on a body of water and it basically ended up vaporizing, life is not going to survive in that. But water is actually a very good buffer of the environment. So the liquid that life exists in water is actually very well buffered from dramatic temperature changes by this property of water in a way that no other liquid that's common would provide it. And conversely, not only is that, or I should say additionally, not only the life in the water benefits from that, but actually the water on the earth, because it's such a good basically sink for all of that heat, actually stabilizes the temperature of the land and the air above the land. It is basically such a sink for energy that it sucks up all of the heat that fluctuates around and keeps the temperature of land fairly stable. Now we think that the temperature of land is very variable, and it is, but it could be much more than it was if there wasn't this high ability for water in the oceans to suck up all that heat. So that's actually that plus I think, in my perspective anyway, these three things are the biggest things that allow majority of what we think of as life to exist. You know, there's some calculation that 98% of the living matter on the planet is bacteria. So if these things weren't true, you know, there essentially would be no life on the planet. If it wasn't capable of dissolving all these things in a really unusual way, and ice didn't float and water didn't resist temperature change, there would be no stable environment for which life could exist. Did that ping it? Oh, that pinged some interest. Excellent.
So, I'm going to use the mic. I'm not a believer in intelligent creation or creationism, but I've often wondered about the arguments that people make about proof for a designer, an intelligent designer. One of the famous ones that's used is the eye, the structure of the eye, in which intelligent design advocates argue that something as complex and well adapted and functional as an eye could not have possibly evolved by accident.
Right.
But I've often wondered about these characteristics of water that you're describing, and which, you know, if you add one other unique characteristic, or I don't know how unique it is, but water is very old, and it probably started to exist after the second generation of stars produced oxygen. And so it's one of the oldest compounds in the universe. And I've often wondered why you wouldn't say, well, here's the real argument for a designer. You really had to be a master creator with a great deal of control over the universe to set these properties in the way that provides the degrees of freedom which made life possible in this way. What are the chances that would happen accidentally, you know, that all those settings would be correct, would be adjusted just right? So my question is actually, would you care to take, you know, a wild statistical guess about the chances that all of these properties were just set by accident?
This is really not my area at all, so that'll be my disclaimer for the YouTube audio. And I was wishing that I had read all the books that I had meant to read in my long list of things before I got questions like that. But I wouldn't care. I've heard all those arguments, and I know there are rationales around all those things. You know what? This is actually one of the areas I think where I've often found that these kinds of discussions are driven by non-scientists in the following way, which is that in my experience, working in science, the science is much more kind of trial and error and empirical than what the popular conception is of it. That's, you know, this has been my experience that that's how it is. Vaguely recalling things that I've read, I don't think you can disprove that. That's, you know, the idea that it was all design can never be disproved, right? So you could never prove it either, but yeah, I don't think you could ever really disprove it, because you'd always could just imagine some slightly more complicated reason why it gets around all the data that you have. So very possible, I think, from my perspective. I wouldn't hazard a guess about what the odds are. I have a friend of a friend who's a cosmologist and probably would. The one argument that I've heard that could probably say you can't even guess the odds is that you could also imagine that when things started, there was an infinite number of possible combinations. But this is the only combination that supported the emergence of life. So what the odds are actually is hard to say. They certainly are very high in this particular configuration of the periodic table. But you could imagine other configurations of the universe, or you could posit them, that because they don't support, you're never around to ask the question. So I don't know, actually. It's a good question. I know there's people have written on it, but I don't know the answer. Easier question. There you go. Good.
Commenting on what Brock just said, I took chemistry in high school and college in the 60s, mid-60s, and to the late 60s. And then I was a science teacher also. And one of the neatest things about being that old is the periodic table was very limited back then. And our teachers shared with us as we were, being taught and learned things on our own, all these different elements were going to fit in mathematically and with the molecular weight, the mole, the atomic weight, and so forth. And that was, for me, a really, it just seemed like a statement that there is a God, there is someone who put this all together, and the proof that there might be a God is that all these elements have been found in all these years, and they all blend in beautifully together. That was really fun, and it's been really fun for me to watch as they've been found.
Oh, thank you. That's great. And thanks for the question. That got us rolling, so that was good. So I only have one more of these slides, and then I just have kind of a little speculative thing. So the other element, I was putting this together, I was trying to think about, what would I identify? There's lots of things that are unique, but what is really kind of unique and relevant for this kind of theme of thinking about kind of water as it relates to, life and our life and human lives and physical components of that, spiritual components of that. The other one that I think is kind of interesting and important for this discussion is that I'll just explain what these words are, and I'll just assert to you that water is unusual in it. More interestingly, what it means. So adhesion refers to the ability of a substance to stick to something that is not it. So adhesive sticks to things that are different from each other together. Cohesion is actually the ability of a substance to stick together with itself. Co usually means together or joint. And then surface tension refers to if you have a liquid. This is one of those things that's almost hardest to understand from a lay perspective, that water has a very high surface tension because we're used to seeing leaves float and little bugs float and specks of dust float on the surface of water. But that property of water actually is really unusual for something of its size, again, and of its place in the periodic table. And so you put the three of those together, the unusually good ability of water to stick to other things, combined with the unusually good ability of water to stick to itself. So water, easiest way to think there is like water beating up on the hood of your car after it rains. That's an unusual property for something the size and properties of water. And then surface tension. Surface tension is most, from people like me growing up in the Midwest or Daryl from the South, there's ponds in the summer, and in addition to being constantly killed by mosquitoes, there's all these little bugs that like zing around all over the surface of the water. Now, that's really unusual. There's very few other types of liquids that could support that much weight on them. So you put those together, and you get what I think everyone will recognize perhaps from their old science days in school, the classic experiment of taking dye in water and sticking a celery stick in there. And then the dye water will just crawl right up those little veins in the celery stalk. That's called capillary action. There's other ways in which we do that, but that's the easiest way to understand. That's just simply the ability of the water in here, the dye dissolved, and other liquids probably couldn't do that, to actually stick together and at the same time stick to the inside of that tube and basically crawl up that surface. And what that means, other than being a fun science experiment, is that actually if you think about how plant life exists, plant life, unlike something that lives in water can just absorb everything from the water. But the majority of a plant is obviously above the ground, and though this part up here needs to receive water from somewhere, and unless it's continuously raining, that's not going to happen very well. And it needs to receive nutrients, and nutrients don't float around in the air. They're either in water or they're in the earth. And so the way that happens is through the capillary action of water from the ground, doing just like it does in the celery stick and crawling up through that trunk of the tree into all the various parts of the tree and supporting life. And so this is one of the more important elements of water. These are these sort of macroscopic properties here basically allow there to be complicated plant life on land. So this is really, if you think of, or if you believe that life on Earth had a progression from the ocean to the land, in the absence of this property, there's really probably very little chance that that would have happened, other than the very, very simplest kind of ground dwelling form. So this is another very important and unique. The degree to which water displays adhesion and cohesion and surface tension is unusual, and then having those all three together is even more unusual. So water is a very unique substance in that respect. And so if you kind of put all of these together, this ability to dissolve, this ability of ice floating, this ability to resist temperature change and buffer whatever is in the water from extreme temperature changes, and this ability to sort of stick to other things in itself and to sort of beat up into discrete little sizes, it really is a very unique molecule. There's no other molecule that commonly exists that is anywhere close to this combination of unique properties. So this is what we mean when we say water, just from a scientific perspective, is really a unique and unusual molecule.
Do these three properties, either in concert or any of them, have much to do with the structure of cells and the likely evolution of cells?
Let's see. Think about that. Probably not. I think actually, so I'm not saying that this is what you should believe or even what I believe, but if you assume that, if you say that life came together in water and a cell had to form, that actually is driven more by basically a cell is like a fat sack. It's like a soap bubble in a way. It's like a fat sack around some water. That's probably driven more by the properties of the fat than it is by the water. Basically, that little bubble encapsulated whatever it was in. In that case, it happened to be in water. Now, what you could say is that this property is probably more important for that, because in order for that, those fats floating around to ball up into a bubble, they had to be dissolved. And so this property is probably more important for the ability of the cell to form. More complex life, like it's particularly land-based plants. That's more important.
Thank you.
So I put in 2 slides here, all for Daryl. So I think that one of the more enjoyable things about developing friendship with Daryl has been our ability to share kind of crazy, whacked out science fiction movie recommendations for each other. Which I have to admit I was into much more when I was younger, and then kind of not for a long time, and I kind of had a revived interest through Daryl's enthusiasm. So that's been great. So this one was mostly for Daryl. But I actually thought it was kind of interesting when I thought about it. I'd never really thought about this before. So water's properties not only may be important for our lives and the lives on our planet, but actually kind of in a weird little coincidence way, may have some uniqueness in terms of helping us identify if there's any other life in the universe, for the following reason, and that is, essentially, despite what you'll see in almost every movie or every TV show or whatever, space is, I don't know if any of you are fans of Hitchhiker's Guide to the Galaxy. I'm not, but someone I know is, and so I watched it. There was a very funny line in there at the very beginning of the movie. It says, "Space is unimaginably big. You just can't imagine how incredibly big it is," which is very true. Space is gigantic, and essentially it's not only gigantic, but for those of you that saw that movie that was just out, Gravity, it is extremely hostile. There's nothing there. Probably the most unforgiving environment that there is, actually. And so what that means really is that in addition to being extremely vast and extremely hostile, that the actual ability to travel beyond tiny, tiny little distances is probably very unlikely, ever. It's vast. The amounts of energy that you would need to sustain life and transport it over those distances are, literally astronomical. So it's very unlikely. But you could imagine at least that we can send energy. We've done that. We've broadcast radio waves and television signals, and we listen for other things. So communication is at least theoretically possible. Now, what's interesting about that is that, that's a little small. When we refer to that periodic table. So that periodic table shows you all the various elements, so these most irreducible components of matter that exist on Earth and in the universe. And to your point, that bottom row is predominantly things that are man-made. Those things are actually generated synthetically. And so, one of the things that may be unique about humans is we've actually created novel matter in a way that never existed. So that's very interesting. We think of the world as this. If you had sort of the ability to conceive of and see the universe as a whole, the vast majority of that universe, in terms of the matter, is simply just hydrogen. The simplest element of all, single proton. And so that is essentially, you kind of do, if you sort of make approximations, I'm sure you taught your students how to make approximations. If you approximated the universe, basically just a giant thing of hydrogen. And we're just in the noise. We're kind of a blip. But if you were an astronomer, study the structure of the universe, you would study the matter of the universe, and the simplest way to do that is to study the thing that is the majority of the universe, which is hydrogen. So you would study hydrogen, and you would develop techniques to study hydrogen, because that would be your way to understand the structure of the universe, and understanding that structure over time tells you about the history of the universe. Radio astronomy, which is exactly what it means, which means we think of the radio as the radio, but actually the radio refers to as a range of radiation frequencies of a certain length. That's the radio band. For a lot of reasons, don't really matter for this discussion. So, an astronomer on Earth or somewhere else, and you'd done your long equivalent of graduate school here or whatever else there is, you would study hydrogen by studying the radio frequencies, or you study the universe by studying the radio frequency of hydrogen. And if you're, like I said earlier, most scientists are very empirical and trial and error. So I guarantee you any scientist that exists anywhere is sort of messed around in that space. And at the radio frequencies around hydrogen, and you compared it to the sort of spectrum of radio frequencies that exist, you'd actually notice that there's this little kind of quiet place right next to the radio frequency of hydrogen. And this is actually right near, and this is, I think, just probably a coincidence, but it's right near the radio frequency of water is H2O, or HOH. If you took that molecule and you split it apart into an H, hydrogen, and an OH, they each have a radio frequency that's very near each other. And in between them, there's basically a gap. There's very few natural radio frequencies in that gap. Whereas if you look at over the entire frequency of radio waves, they're pretty populated. So it's imagining that it's kind of full, there's hydrogen, kind of quiet place, OH, and then it's full again. And so because it's HOH, H2O, it's called the water hole. And so because on the other hand, you said, hey, I'm an astronomer somewhere, and I want to send a radio wave. Know that the radio wave spectrum is very, very populated, except for this one area. Well, then I'm going to broadcast in that one area, because that's going to be where somebody can hear. Other intelligent astronomer somewhere else, and unless you have a totally different concept of logic and a totally different view of the universe, you're going to make that same calculation and take it one step further. If I want to listen to for somebody broadcasting, I want to listen in the same place. And so that's why, in fact, right? Thank you. It's based on this thing. The real project that was funded for many years by the government, no longer, and now I think it exists on private funding. And that basically the premise of SETI. SETI was going to listen for radio waves throughout the known universe, in all directions, I should say, in the known universe, in that one area called the water hole. And so I just thought that was kind of interesting kind of wrap up. Property of water, actually, I just turned it off. Luckily, I've done this before, and so I know how to turn it back on. That property of water, interestingly enough, has nothing to do with any of the other properties of water that I told you about. In fact, most of those properties about water have nothing to do with each other. So it's really this very unique combination of things, completely from a technical perspective, that make water very special. And also, I think, not only for our life, but for this last point here, maybe potentially for our ability to understand kind of the full conception of what life could be. So that's really all I have, and I guess we have 10 minutes for questions at least, or Daryl. So otherwise, anything I could answer about any of the things that I said today? I've forgotten everybody's name, so I'm just going to point.
Well, if water solves proteins and so forth, how do animals not dissolve?
That's a great question. And that's because, this gives me a chance to tell you my most interesting thing of the recent times. So every year, if you imagine, and I may be going too simple, so ignore me if I'm not. So we're made up of cells. Cells are like little components. Each of those cells is basically, oil and water don't mix. And each of those cells is essentially a little fat droplet with water on the inside. And the way that those things actually stay solid is that we have protein that's sort of packed into that fat envelope on the outside. That gives it its structure. That's actually more true for bacterial cells than it is for human cells. Human cells still have the same components of proteins and fats in that outer envelope, but there's relatively fewer proteins, so they're a little less soft, or a little more soft, and that's why animals don't dissolve, because we have that structure to each of our cells, and they all combine together. And that gives me a chance to tell you my most interesting fact of the night, which is that one of the things that I do in my research group is we do some work on understanding how the bacterial contents of your intestines actually affect your health. And there's actually a lot of great evidence recently that even things like heart disease are driven in part by whether or not we have certain types of bacteria in our body that take certain things out of your food, convert them into something which goes into you and then causes heart disease, and how we can intervene in that. And in the course of getting ready to do this project, I learned some really interesting things, one of which is you sitting there right now, you are a compilation of about 10 to the 15 cells. And only 10% of those are actually you. 90% of them are bacteria that happen to live as part of you. So in fact, all of us here are really only about 10% human. Or, the other way to look at it is that all of us are essentially a kind of hybrid organism, or a so-called commensal organism. We consist of things that carry our own genetic code, but we also consist primarily of these vast populations of microorganisms that live kind of in us and on us. And those proteins actually that in those bacterial walls are much stiffer because there's so many more of them relative to the fat. That actually gives a lot of their structure and gives our cell structure as well.
One other question. You start off with a periodic table. Hasn't scientists expanded beyond that to sub-parts of?
Absolutely. I made a simplifying sort of view or assumption, but you can certainly go below the level of the atom, and you can get down to the components of a proton and neutron and electron. So protons and neutrons make up the so-called nucleus of an atom, and electrons go around it in a cloud. And then you can go one layer lower than that, and there's, I'm not a physicist, but I think there's on the order of 6 to 8 subatomic particles, and various combinations of those make up either a proton or a neutron. As far as I know, that is the lowest level of division of matter that you can go to. Those have properties that are not very intuitively understandable, whereas things at the level of an atom or an element, they're more intuitively understandable in terms of we can describe them in properties that can relate to something that we know more commonly. Like we can talk about them in terms of charge, things like positive charge or negative charge. We all kind of understand that. But the way that you describe a subatomic particle is very mathematical. It's not very intuitive. So for the purposes of this kind of discussion, I just kept it at the level of an atom or an element.
When you just spoke about humans being 90%
See, you love that too. That's awesome.
bacteria,
I love this fact.
I'm just gonna throw this out there. I'm gonna presume that everybody really knows this, but just in case you were freaking some people out or little kids listening, bacteria is both good and bad.
Oh, absolutely. And since there may be people other listening somewhere at some point, presumably, I would imagine, presumably the large majority of probably almost all the bacteria that we have is at least a neutral, and it's probably a positive. I think most likely what the purpose of most of the bacteria in our gut is we tend to think of ourselves as modern humans, and even 10,000 years ago we were modern humans. We could cultivate grain. But you go back 50,000 years, and if you believe that that's how far we go back, and 50,000 years ago we were essentially virtually starving to death cave people. And the two most likely things, the reason we can reproduce sometimes, unfortunately, at very young ages, is because the odds that a human would live past predators, or starvation were pretty low. And probably the major function of gut bacteria is because bacteria can digest lots of things that we cannot. For example, we eat salad because it's empty calories. And why is it empty calories? Because we can't digest it. But in fact, bacteria can usually digest all sorts of plant material. And most likely purpose of that was to provide calories that the human could absorb. Because in the absence of that, people would probably just starve to death. There isn't enough easily digestible calories in the natural environment for a human that didn't have this complement of 10 to the 14 bacteria in its gut that could convert all of that food stuff into more digestible. There's some estimates that they provide about 20 to 30% of your energy content. And so that doesn't matter to us because we can go to McDonald's or whatever, but if you were on the edge of starvation, that 20 to 30% is probably the difference between life and death.
So just continuing that discussion about the bacteria, the poet W.H. Auden, I think it was probably in the early 70s, read a Scientific American article, which really didn't describe the gut bacteria, but described the various zones of the body that supported different kinds of bacteria. And this was pretty new at that time. And he was so inspired by this that he wrote a poem in which he addresses all of the bacteria on his body and basically says, I know you have to be there, and he refers to the places where they would be living in sort of metaphorical, poetic terms. And I just want to get along with you, but on the other hand, you could think of me as your God, because my fate will, determine your fate. Or maybe it's vice versa.
Right.
But anyway, if
Probably
you're
some of
interested
both.
in that, it's pretty, I think you can find it online.
Sometimes it is vice versa, because if you, for example, take erythromycin because you're sick and you need an antibiotic and you get a severe stomach ache, it's because the bacteria that is not good is conquering the good. So all you have to do is go and get a live cultured yogurt. And then it all comes back and you can keep taking that medicine. So there's a yin and a yang there.
Thank you, Chris, so much, man. That was very cool. Very, very cool. Really appreciate it.